So welcome everyone. So far we discussed on the ISA and we compared different ISAs and talked about various trade-offs. In today's lecture we'll start considering a real ISA based on RISC architecture, namely the MIPS ISA. This ISA is based on load store architecture and has a relatively simple set of instructions, so it's worth studying that. We'll also learn about how to write assembly code for this ISA. The other ISA that I want to touch upon is called the hypothetical CPU, HCPU ISA. This one is not a real ISA, but it might be useful to go over it to compare against MIPS architecture and MIPS ISA. HCPU ISA is based on memory architecture and has enough number of instructions to write assembly code. This HCPU ISA can also be considered as an example for you so that you can compare both of these ISAs and come up with your own ISA design, which will later can be advanced by adding more instructions. So let's go through the outline of today's presentation first. So the outlining goes, we start with discussing the general form of the assembly code. We'll discuss MIPS ISA, the load store model, give you some examples, and MIPS simulator, the Qt SPIM. And as I said, the HCPU could later be used, but we're not going to be discuss that because we don't have time for that, but maybe next or future class topic we can consider that. But HCPU, as I said, could later be used as a baseline to structure and architect the MIPS CPU, which can be taught the next year computer architecture class students. I'll try to assign some work on that to those of you who are interested in it. The general form of an assembly code includes instructions, operands, addresses, labels, comments. The example shown uses the MIPS language mostly, and this is how it looks like. In this presentation, I highlighted with blue light, the light blue of the rectangle, the instruction of the code. You can see where the instructions are located in this code by looking at the blue highlighted rectangle. Next, I highlighted with light purple the operands and registers. This highlighted region also includes labels like L1 and L2. These labels are locations in memory to depart from or arrive at and resume the executing the instructions. Next, the light green shows the labels as seen from the program counter. These labels are actually where breakpoints are in the program. Mostly they arise due to conditional statements in the program so that the program can jump from one label to another before exiting the program. Next, we see the comment section shown in yellow and hash sign to disable these comments from being seen by the assembler. This comment disable symbol, the hash symbol, could be different from one assembler to another. The assembler for the MIPS ISA we will adopt in this class uses hash sign to disable comments. Here are some of the instructions which are to execute arithmetic operations, and these are shown in red rectangles. And on the other hand, the other instructions, like control instructions, tell the program to branch or jump due to conditional statements in the higher level language. Or it's the end of the subroutine or an interrupt call. And that control functions are actually shown in black boxes in the slide. So the MIPS, the MIPS stand for microprocessor without interlocked pipeline stages. So we haven't come to the pipeline, discussing pipeline yet, but when we design and when we talk about pipeline, we will see that they can be interlocked. And MIPS, basically, for the sake of keeping the microprocessor design simple, it does not use any interlocked in the pipeline. So RISC ISA is developed by MIPS Technologies. The early MIPS architecture were 32-bit and 64-bit versions added later. And some of the names of these versions are MIPS 1, 2, 3, 4, 5. And there have been 32-bit and 64-bit versions as well. MIPS is a load store architecture, as we have spent, I think, a couple of minutes discussing that before. Here is the instruction format for MIPS. Three basic formats. We have the register type, immediate type, and jump type. Since it's fixed size and uniform ISA, it's simple to decode. And the code size is fixed to be 4 bytes per instruction. The memory, on the other hand, must be 4 bytes aligned. What does that mean? Well, that means here's an illustration, the picture, to show you that how an unaligned versus aligned memory looks. You can realize that in the unaligned case, When the program counter shows the beginning of the instruction, we will need 4 bytes to read, and that leads to read a single byte from the next line in memory. So this means like the last 3 bits of the program counter must be adjusted accordingly. Instead, if we could align the instructions such that they are stored in memory lines and do not spill over other lines, in that case the least significant 2 bits of the program counter needed to change and compensate for reading instructions. So you basically have to change only 2 bits. In fact, the program counter must be incremented by 4 to be able to read sequentially the list of instructions from the memory. MIPS ISA is format, and the fields in the code are clearly seen and easy to extract in the hardware. And next, as we mentioned before, MIPS memory is byte addressable, and so using 32 bits to address the bytes, it means that we have a limitation in total number of bytes to store in the memory. This number is 4 gigabytes, and the address of memory lines is shown using hex notation in this slide. Here's the set of general purpose register names, their indexing usage, and whether they're preserved or not. These information can be found actually on web. It's available to everyone. The general purpose registers are user accessible registers. Some of these registers are special purpose and some of them are completely temporary and can be used for any workload. For example, before calling a function, we store inputs to the registers A0, A1, A2, and A3. That's kind of customary to use. And after executing the function instructions, we make sure that we put the result in the output registers such as V0 and V1. V0 register has also another special usage, and we will explain that when we discuss system call or syscall instruction. There are also registers that are not user accessible. For example, the high register or low register, HI and LO registers, which are used to help multiplication and division instructions, as we will see later. For MIPS, we will have cheat sheets and other information uploaded on Blackboard, as well as distribute them in class. So you will have the summary of instructions and details about using these instructions. Yet, I'll try to cover some of those instructions in this lecture so that you will have some familiarity by the end of this video. Here are the types of instructions for MIPS. Computational, which includes arithmetic and logic operations like addition, subtraction, multiplication. Load store instructions that are necessary to writing and reading to or from memory, like load and store. And also jump and branch instructions that are there to control transfer, also used for conditional statements. There are also other types of instructions, advanced, such as vector instructions. So I would recommend you guys to see the handout for the summary of these instructions. All right, here's an example of add and add IU, which stand for immediate unsigned. I've also shown here that temporary registers are used to implement functions like the contents of T1 gets added to the contents of T3 and the result is stored at in the register T0. I also have shown you an arithmetic operation, down there, and the corresponding MIPS assembly code to execute the operation. Suppose that the contents of registers from S0 to S7 have A, B, C, D, E, F, G, and H in them, and you have to just use the assembly code shown at the bottom of the table to be able to compute the results, A and F, and store the results in the corresponding register locations. I've also shown you the load immediate instruction that loads the register T0 and T1 with the code shown in hex notation. Think about the contents of T2. What would be the contents of T2, for example, after NOR instruction gets executed? More instructions. So load immediate instruction, for example, is divided into 2 different instructions in the assembler. These are LUI, load upper immediate instruction, and OR immediate instruction, as shown. This will make actually the LI, load immediate instruction, as pseudo instruction. And LUI and ORI, they are, on the other hand, real instructions. The pseudo instruction are interpreted by the assembler and replaced by the set of instructions needed to execute that particular pseudo instruction. There are also other types of instructions, as I said, that requires user unaccessible registers like division and multiplication. And there are, as I said, 2 registers not exposed to software level and reserved for multiplication division, namely HI and LO. Multiplication of two 32-bit numbers generates 64-bit number. So the most significant bits, 32 bits, are actually stored in HI, and the least significant 32 bits are stored in the LO. For division, the HI stores the remainder, and LO stores the quotient. Yet another instruction is called set less than instruction, SLT. This instruction sets T0 to 1 if the contents of T1 is less than T2 or 0 otherwise. Another instruction is called the load byte instruction. It fills the contents of the register with another register called the base register value plus the offset. So here are some examples with unsigned as well as signed numbers. They're only different in the way they treat the signed bit. Finally, system call instruction causes a system call exception, which the operating system catches, interprets, and usually returns from. This service is a software interrupt, unlike the other hardware interrupts, and it's initiated by the operating system only. So let us go over the examples. Here is an example. I've got 4 inputs, and we were considering a function, and those inputs are stored in registers. Let us assume that they are stored in registers A0, A1, A2, and A3. Please also pay attention to them being unsigned and signed numbers. So we start calculating the A star B, which is L multiplied by B, which is the multiplication of A0 and A1, and the result is written to the LO register, right? The low register, because A and B are actually signed integer type, right? So they actually consume 16 bits. So the multiplication can only be 32 bits long. The contents of high register is also 0. So we move the result from low or temporal register T0, and next we add the result in T0 to A2, which holds C, and the right result to A0. This sum instruction accepts 3 addresses. Some of them 2, and some of them only 1 address. You can figure the rest of the instructions yourself. Here one note is that the final instruction jump RA, the RA register, which means after we're done with the function, we return to where we started. In other words, the address that we were originally coming from, and which is stored in the register RA. So we jump back to the main program and continue executing instructions. So here are 2 other examples. The top one shows a function that swaps the values at entries k and k plus 1 of the array provided in V. And shift left operation by 2 is used to multiply the index by 4 because the memory must be aligned in MIPS, as we discussed earlier. Note here that register T0 is the temporary variable, and register T2 is yet another register that holds a temporary variable that's not explicitly expressed in the C language. Similarly, the example below show how we do the branching while implementing if clauses. Just work through the details of this example to convince yourself this assembly code does indeed execute the necessary set of instructions for the conditional statements shown to the left of this slide. Here is yet another example for MIPS. Different from previous example, this one has system call as well as directives like the string and dot data, also dot text. These directives are basically telling the assembler that the rest of the code is the main text or data, etc. So system call can execute multiple things in MIPS computer. One of them is printing a particular data type such as integer or floating number or even a string. The other functionality could be reading from I/O devices or exit the program. So these are summarized in the table shown. In order to choose among these operations, you need to set register value V0 to some number, as well as register value stored in A0 or F12 if need be before calling system call instruction. So for example, if you want to print integer value, you have to first set V0 to 1 and A0 to integer, and then call system call to print the integer value, which is stored in one of the registers. So try to figure out what this code that is shown to the left of the table do. Finally, I want to talk about the software that is actually designed to emulate simulate actually the MIPS ISA. That's called MIPS Code Simulator. This particular simulator actually emulates the MIPS microarchitecture and assembles the code you wrote by loading the .s extended files. It's an open source free software that you can download from the link below. I would recommend you to use this software while testing your assembly handwritten code. So in this class, we covered briefly what MIPS ISA is and discussed the details and the format of the ISA, the memory architecture, as well as the example codes that you can write using MIPS instructions. We have also mentioned about one simulator that can accept the assembly code written for MIPS and simulates an appropriate microarchitecture to produce results and writes the output of the corresponding memory locations. As indicated in the outline, MIPS is load-store model. We have another ISA that we will discuss in the next or one of the future classes that will be based on memory architecture, the hierarchical CPU, the hypothetical CPU ISA. We will soon start discussing microarchitecture, single-cycle, multi-cycle computers, and you will see how these ISAs can be implemented by facing a variety of design choices and freedom. So please feel free to drop any questions you may have about today's lectures into my email box, and I'll be more than happy to help you with your question. Thanks a lot.